And again, as I said, this algorithm is not as stable. So I'm going to show that in an Excel sheet. So I'm going to bring up my Excel sheet here, and I'm just going to, let me share that as well before I forget. And I'm sorry that I have a, I don't know, little baby, and sometimes you may, I don't know if you can hear him or not. Sometimes he just come and knock on the door and he wants his mommy. If you hear his noises, I'm sorry about that as well. I don't want to record everything just because of that. And so hopefully that's not interrupting you guys. Okay, disturbing you guys, I mean. So anyway, so a stable algorithm. So again, as I said, the definition of an algorithm being stable means that the algorithm is going to keep its relative order of its input no matter what, right? So, and what we mean by relative order. So imagine the data are coming, and here are my data. So then I'm going to put the index of the data that are coming, right? So this is data number 1. This is the data number 2, data number 3, and so on, right? So the first data, for example, is, again, we're just following the book as well. So the data are coming with numbers. So first I have like 4, and then we have 2, and then we have 7 or 6 and 7, and then we have again 4, and then we have 1, and then we have 2, and then, sorry, 2, and then we have maybe even another 2, right? So I'm gonna go look all over here. So you see that so these are the data that's coming, right? So these are the index of this data, and when I'm trying to sort this data, right? If the algorithm sort them in a way that I have 2 4 here, right? So, and I have 2 2s, and I have 1. So this is how it's going to be sorted. Right? The 1 is definitely going to come here. Then the 2 has to come, but then this 2 came first already. It has a higher order, and then this 2 came, and then the other 2, right? So this algorithm is going to sort them, and not only is going to sort them, it's going to keep the relative order. So first data 2, then data 7, and then data 8. Although the value of all of them are the value of all of them are 2, but it's going to keep the same exact order that they come, right? The relative order. So this was very first, then this one, and then this one. So it's just trying to sort this data. Is also going to keep the relative order between this the same keys, basically the same values. And then the next one is, for example, 3. We don't have any 3, we have 4. So the data 1 4 came first, and then the data 5 came, right? So that means that's how it's going to sort it. If an algorithm sorting this like what we see on this example, then this is going to be in a stable algorithm. Otherwise, we consider that not as stable, right? So basically, again, the relative order of the data should stay the same. And so, for example, an application of it. So you imagine you're sending a text messages to your friend. So the text message is going to have a destination and source and destination IP or number on it, right? So the packet are going to go with this exact specific order, right? So you're writing a message is long, it's going to break it to 2 different text messages. It's not going to be able to send them all in one text message, right? Sometimes if it's a long message, sometimes you only have, like, for example, 256 characters that you can send. So if your message is longer than that, then the sender, it's gonna, when it's trying to transfer that, it's going to break it to the smaller packets, and it's going to put the number on them. So they're all going to go to the same destination. They have the exact same source, but they have the packet number, right? So because it's going to break them, so it's going to break them to, for example, 3 packet, 1, 2, 3. When it gets to the destination, they have to put them back together in the same exact order, 1, 2, 3, and then they're going to show it to your friend. So what is going to happen? They're not going to go on exactly same route as well, right? So some of them are going to go to different routers in different places and different hubs of whatever you want to call them, and then they're all going to at some point get to the destination. So the destination is going to get those data and then going to sort them, and then it's going to put them together and make a one nice text message all put together, and then it's going to show it to your friends. So for that kind of applications, for example, as you can imagine, the relative order is very important, because they need to know exactly how they're sent out, so they can sort it back to the same exact kind of shape. So 1 to 3, although they have exact same destination address, right? So the relative order sometimes can be useful. So there are other applications for it maybe, but this is just came to my mind. So if a sorting algorithm is able to do that, then we call it stable. If not, then it's not a stable algorithm. So as you can see, this selection sort that we have here is not a stable algorithm, and it's not an adaptive algorithm. It doesn't matter what types of input you're using, it's always going to use the same exact performance. So the next algorithm that we're going to see now is going to be the insertion algorithm. So again, let me make sure I switch my slide to switch my page to the slide. So this is going to be our insertion algorithm. So insertion algorithm is also kind of acting the same as far as the fact that it's trying to sort, finding the minimum and put them in this. So basically it's going to sort from the beginning of the list. It's going to find a minimum and try to put it in the beginning of the list. But in order to do that, it's using what we call a sublist. So it is starting with a very small sublist. It only have one single element in it, and that's the element in index 0. And then it's going to keep growing it by going to the original list, right? Not the sublist. So here in the first line, the original list shows as the black, and the sublist shows as red. So the sublist only have element 2 on it, and the sublist is always going to be sorted. So when you have only one element in the list is always sorted. As you keep adding element into this sublist, we want to make sure that the list is staying sorted, right? So that means when I'm trying to find a next element and add it into the list, I'm trying to make the list sorted. So the next element that I have to add to the list is 9. So when I'm trying to add it to the sublist, I'm going to compare that with 2. If it was a smaller than 2, then it has to be shift. If it's not a smaller than 2, it's just going to add it to the list, right? So as you can see, 9 is going to be added to the list, but we didn't do any shifting. The next element we have to add to the list is 5. But we're going to add the 5 into the list. We have to first basically compare 5 with 9. So 5 is less than 9, then we have to do shifting. But 5 is not less than 2. So it's only going to have one swapping or shifting there. The next element we're going to add to the list is going to be 4. So 4 is smaller than 9, is smaller than 5 too, but it's not smaller than 2. So it's going to be only having basically 2 shifting. And then the next element that we're going to have is 8. So this is smaller than 9 only, so it's going to do the 1 shifting, and so on and so forth. So basically, again, we have a sublist that is always going to be the sorted sublist. And as we're going to go to the original list and we keep getting elements and we add, as we inserting this to this sub list, we want to make sure that we're making this list sorted. And as we, when we're done, we're basically entire sub list become the whole list. That is a sorted list now. So let's look at the animation of it on the website of the book first. It's right here. Sorry, it's right here. Insertion sort. So the sublist only have 91 on it, then it's comparing it with 39. We're going to add 39, and so we're going to have a shifting 63. It's only going to be less than 91, so we have only one shifting. Here we have shifting like all the way because we have to put it at the beginning of the end. So you can imagine if I have to do that for every single element. And we're starting with a one, and then we have to keep comparing that one with the rest of the list. That means we still have a like nested loops here again, right? So we have the same concept of nested loop, and that is still going to act as in a square. And also just by looking at it, so if the element that we find is always going to be in a reverse sorted manner, then that means we have to always put them in the beginning of the list, which index 0, and that means we have to shift everything. So that means it's a worst case scenario for us, and that tells us that this algorithm it's actually adaptive, right? So if the list is reverse sorted, it's really going to act really bad. So let's, you can see how it works, right? So okay, so I guess you're getting the idea. Now look at the